Welcome back to the exam walkthrough. We're going to be going through question number 17, 2024, June, part B. So let's continue it now. So it says after some time, the charge on the spacecraft will be 1.5 times 10 to the power of minus 6 coulomb, and the same charge will be on the satellite as well. And it says calculate the minimum energy in joules required for an electron leaving the surface of the spacecraft to reach the surface of the satellite. Assume the charge on each does not affect the potential of the surface of the other object. Okay, and they've given you the radius of the satellite and the radius of the spacecraft. So first, let's identify what's happening here. Okay, I'm sure many people read the question, but then they don't get what's going on. So this is going to be positive, negative, and we have electron that's traveling from this point here to this point here. So the first point clear? Okay, that's the first thing I want you to understand. Electron is traveling from here to here. The second point I want you to understand. This is a positive charge. When the electron is here, okay, there is going to be an electric potential value here, right? Let's say that electric potential value here is 9 volts, okay? Now, that's going to be negative. 1 second. This is supposed to be negative, okay? Now, what they have told you in the question is assume that the charge on each does not affect the potential at the surface of the other object. What does this mean? This means that this 9 volts that we have is because of the positive charge. Now, because of the negative charge also, there will be an electric potential value. Maybe that electric potential value is minus 2 volts, right? Because the distance is more, so the electric potential here would be less. So it would be minus 2 volts. And then you add both of them, you get the electric potential at this point as 7 volts, right? That's how we usually do it. We add both the potentials due to both of the charges, and we get the final answer then as the electric potential at that point. But here they told us we don't care about this minus 2 because of the other charge. Okay, they told us they don't affect each other. So that minus 2 and basically the electric potential due to the other charge is not here. Okay, and the same thing is when the electron is here. It's going to be minus 9 volts, and there's not going to be any plus 2 volts here because of the positive charge. We only consider each of the charge and their electric potential. Now, we have to find the minimum energy required for the electron leaving the surface. So we need to find the energy that the electron needs to have to go from this point here to this point here. So basically, as the electron moves from here to here, it's gonna gain electric potential energy. So the gain in electric potential energy is equal to the minimum energy. And we know the gain in the electric potential energy is equals to the charge that's moving. So here it would be the electron, the charge that the work is being done on, or that's gaining the electric potential energy, Q, that would be the electron, times the change in the potential difference. I hope that's clear. Okay. So now we just have to use this formula and we'll get the value of the minimum energy. So the change in potential difference. So we have to find the potential difference here and the potential difference here. So we just use this formula and we get the potential difference as both of the points. So now we have found both of the electric potential at the surface of both of the charges. Okay, remember they've given you the radius already. So this is the distance, the radius basically. And we get both the values as 5,400 volts. Now we find the change in the potential, which is going to be, we're going to start here. So this is the starting position and this is the final position. So final minus initial, minus 5,400 volts, minus 5,400. And that's going to give me minus 10,800 volts. I can just ignore the minus sign. So it's going to be 10,800 volts. And then what I can do is I can just plug it in here. So 1.6 times 10 to the power of minus 19 times 10,800. That's going to give me 1.73 times 10 to the power of minus 15 joules. So part II. Now it's a bit long to read all of this, so I want you to pause the video and read through this carefully, and I'm going to explain it. So I hope you have read the entire question. what's basically happening is we have the spacecraft and the satellite, and they have an electrostatic force. And we have to find that how much time will it take for the satellite to move a distance of 300 kilometers. That's basically what you have to find. How much time will it take? So T is what you have to find. Okay? And the reason the satellite is moving is because there is a force on it. And that force is because of the positive and negative charge. Now, first thing what we can do is we can see what they've given us in the question. They've given us mass, and they've also given us enough values to calculate the electrostatic force. So first and foremost, you're going to calculate the electrostatic force. So force is equals to K, Q1, Q2 over R squared. So you can easily find that out. The charge values were given in the previous part. I've just plugged in all the values now and taken the values from the question 20 here, and then charge is given in previous part. And now all you're going to do is find the answer to this, and you're going to get that as 5.057 times 10 to the raised power of minus 5 newtons. Now they have given you the mass in the question. Okay, so what you can do is you can use F is equals to ma to find the acceleration. So this is going to be the acceleration of the satellite. Now what we can do here is we want to find basically how long will it take to travel 300 kilometers. They have given us the acceleration, or we have found it out using the information they give us, and they've also told us that the satellite was initially at rest. So remember, we're looking at satellites when we're doing all of this. So what we can do here is pretty clear. I hope you get what I'm trying to say here. The acceleration is also constant, by the way, because they've told us the electrostatic force is also constant. Constant acceleration, distance, time, speed. We're going to use SUVAT. I'm going to plug in the values now. So you have 300 kilometers times 10 to the raised power of 3 to make it meters. Initial velocity is 0. Final, I don't know. And acceleration is 2.022 times 10 to the raised power of minus 8. And question mark is the time. So what we can do here is we can use S is equals to ut plus half at squared. This cancels out because u is 0. And now I'm just going to find the value of t. So now we have got the answer as 5.446 times 10 to the raised power of 6 seconds. I'm going to divide that by 60 to change it into minutes. Then I'm going to divide it by 60 again to change it into hours. And then I'm going to divide it by 24 to change it into days. So 60 times 24. And that's going to give me 63 days, which is approximately 60 days. So student, or I'm not sure who said this. So the scientist. So scientist is correct. So now for part C, in reality, the magnitude of the positive charge on the spacecraft may be greater than the magnitude of the negative charge on the satellite. Suggest why. So let's look at the spacecraft. This is the spacecraft. Why is it not drawing? Okay. This is a spacecraft, and this is the satellite. Now, electrons are flowing from the spacecraft to the satellite. And remember, electrons are being lost by the spacecraft, so it's getting a positive charge. And the satellite is gaining those electrons and becoming more and more negative electrically. It is possible for some of these electrons not to be gained by the satellite, but instead they miss the satellite. So maybe they miss the satellite and they don't hit the satellite. Because of this, the satellite doesn't gain that electron, so its charge doesn't increase. While the spacecraft is still losing the electron, still lost the electron, so it still got more positive, but the satellite couldn't get more negative because that electron that was lost didn't end up on the satellite. Okay, basically let's take this electron here. It was lost, but it wasn't gained. So it was lost by the spacecraft, but it wasn't gained by the satellite. So the spacecraft got more positive, but the satellite couldn't get more negative. Okay, I hope you got that. So the answer to this will basically be some of the electrons don't hit the satellite. So that's going to get you that 1 mark. Now there are a lot more answers to this that you can check out. A lot of things that the examiner accepts. For that, I'm going to show you now the examiner report and the mark scheme.